Good day, I'm Greg Tucker at the University of Colorado at Boulder, and I'm going to give a short overview of the Community Surface Dynamics Modeling System, or CSDMS, which is sometimes pronounced systems with a soft C. First, a little bit of history. Systems was established in 2007, and it's now one of 3 NSF-supported facilities that support computational modeling within the geosciences. The other 2, of course, being CIG and our atmospheric colleagues at CESM. So CSDMS supports a broad community of Earth surface scientists, people interested in things happening at the Earth's surface, works in 3 areas to support that community: computing support, community development, and education. We'll start off with a few comments about community support. Systems supports a large community. It's up to close to 2,000 members at the moment, spanning 72 countries, several hundred institutions. The core support goes to support a small integration facility here at the University of Colorado. And the kinds of questions that people in this community ask are diverse. A lot of different kinds of things that bear on soils and sediments at the Earth's surface. So they range from engineering timescale problems like natural hazards related to things like landsliding or flooding, all the way to geological timescale problems related to things like topography and sedimentary stratigraphy. You can see already that there are some obvious linkages with the CIG community in the deformation of the crust and lithosphere and its influences on topography and its reflections in sedimentary stratigraphy. One of the things that CSDMS provides for its community is a model repository. So this is a web-based portal that provides the community a place to share their codes and to use codes that are shared by others. So there are currently over 300 codes, both models and modeling tools, across a spectrum of different kinds of research area and ranging in scale everywhere from a small subroutine to a large integrated numerical model. Each entry comes with standardized metadata and bibliographic information and that sort of thing. Another area that Systems works in is to provide computational support, much of it in the form of enabling software. So the original challenge set by the founders of CSDMS, reflected in the science plan that dates back to 2004, is as follows. The vision was that CSDMS will be a modeling environment containing a community-built, freely available suite of integrated and ever-improving software modules aimed at predicting the erosion, transport, and accumulation of sediment and solutes in landscapes and sedimentary basins, and do all this over a broad range of time and space scales. Now, if you think about this, this is a daunting challenge. This is a challenge worthy of a tech giant and not something that a handful of people at an integration facility can do by themselves. And so it's very much a community scale effort, with the integration facility focused on providing the tools and technology and standards that can take the community's work and make it more interoperable and more community accessible. So pulling off the vision involves 4 sort of key things, and I've listed them here. One is a way to standardize various elements of this cyber ecosystem. One is a way to operate across different programming languages. One is a way to have common tools and technologies. And one is a way to have a common framework in which to pull all the pieces together. I'll say a few words about each in turn. In terms of standardization, Systems has developed what's called the Basic Model Interface. This is an interface specification. It's really just a list of functions which, if added to a numerical modeling code, will allow that code to be easier to learn and more interoperable with other pieces of software. And it's the sort of thing that you might imagine would go into something like this. So the Basic Model Interface includes functions to initialize a model and get it ready to go. Functions to iterate it over time or get it to do its thing. Functions to query data, functions to modify data, which you need if you're coupling models, functions to clean everything up and shut down, and a variety of other functions related to gridding and timescales and units and so on. The BMI has been adopted by a variety of research groups around the world. It's been used, for example, by folks at the USGS for some of their water modeling, by folks at Deltaris in the Netherlands for some of their model coupling needs, by another agency in the Netherlands called the Dutch eScience Center, among others. So the next sort of set of ingredients has to do with language interoperability. There's a variety of different languages used in our communities, and here we've taken an approach that uses Python as a lingua franca and provides a way to access codes written in different languages, in particular C, C++, and Fortran, directly through a Python interface, a set of Python functions. Then in terms of a toolkit, there are many common needs in terms of software among diverse numerical models. And to try and meet some of those needs, we've developed a programming library called LandLab that is geared toward grid-based numerical models, in particular with this version, 2D grid-based numerical models, by providing a set of standardized I/O tools and gridding tools, and by allowing functionality to take the form of reusable components. This slide shows a variety of some of the applications that have used LandLab to date. They include, again, short-term things like flood hydrology and ecosystem hydrology, and longer-term problems like tectonic geomorphology, basin stratigraphy, and so on. So that's a little bit about LandLab. The final ingredient then is a framework to pull the pieces together. Here again, we've used Python as a popular and powerful high-level language, and created what is essentially a basic Python package called the Python modeling tool. And this is a tool that you can use to pull in any of a variety of numerical models, legacy models written in different languages, but accessible through Python using the basic model interface. And it means that you can construct a workflow or create a script that couples models using a Python Python script or a notebook or what have you. So that's a quick summary of some of the modeling tools. I'll turn now very briefly to education, the third pillar of CSDMS activity. We have an education knowledge transfer repository that includes resources like lab exercises, both by and for educators that use models in the classroom, and a variety of resources like webinars that provide a way for community members to teach one another about various technical topics, model concepts, tools, machine learning, you name it. So I want to turn now to some of the opportunities for interaction between CSDMS and CIG. These are two communities that have been closely interwoven in the past and continue to be so. One of the notable activities 2 years ago was a workshop that was held jointly between CIG and CSDMS on the topic of coupling of tectonics and surface processes. From that workshop came a white paper that outlined a series of recommendations for future interaction. It included things like continued community development, such as joint workshops and tutorials, outreach to other communities, as well as areas of common code development efforts. For example, improving the ability to couple models, addressing needs in parallel architectures, addressing needs in confronting models with data, and doing uncertainty quantification. So I think there continue to be a lot of opportunities, and I want to reflect on this. I'll leave you with the following thought experiment in the form of a simple toy model. So this little animation shows a model of erosion and sedimentation around a hypothetical microcontinent somewhere in the middle of an ocean that is being actively rifted. And it illustrates many of the processes that our two communities are interested in. We have tectonic deformation happening here in a simple kinematic way. We have erosion that's exhuming rocks. We have deposition in the form of deltaic stratigraphy and rift basin stratigraphy. And it illustrates that we now have the technology to address these kinds of coupled source to sink problem. And it opens up any number of possibilities for exploring the coupling between erosion, deposition, and exhumation at the surface and the underlying mechanics of the deforming lithosphere and crust. So again, I'll leave this with you as a thought experiment and look forward to meeting many of you at the CIG workshop.